We can start. Good evening, everyone. Today is the 13th session of our lecture series on structural design of highway bridges. And over to you, sir.
Yeah, thank you, Bandhuka. I'm sorry about the delay because we had to attend to this the funeral function of Professor D. Sujeshekara. So I will start sharing the screen. So now last time I explained with the aid of the spreadsheet. Right, with the aid of the spreadsheet, last time I explained the design method. So if I summarize it, first one is select a section, obtain bending moment envelope, assume secondary moments. So assume secondary moments, obtain the final bending moment envelope consisting of MA and MB, and then find limits on ES using EP is equal to ES minus M2 over RP. Obtain EP profile. 7. Get RP EP, and then 8. Fit a bending moment diagram into RP EP, and after that from this work backwards and hit ES. So those are the methods, but there are so many other important considerations that we have to pay attention. So I'm going to explain some of those things with the use of this particular diagram. Right. So now first thing, let's look at the spreadsheet first, and here you can see the spreadsheet. So if you look at this spreadsheet, we have done the calculations, and you can also see now these are the bending moments. Based on that, we can calculate Z1 and Z2. And then we have selected M2 values. Then we have got the final MA and MB values. And then we have selected a trial value of 26,000 with a loss ratio, meaning 30% loss. So the R value is 0.7. Based on that, we have calculated for this 26,000 force, we have calculated the upper limit of ES and lower limit of ES. So after that, using this and the secondary moment and the pre-stress and the loss, we can calculate the corresponding EP upper and lower. Now today I'm going to concentrate a little bit on this particular aspect because last time I skipped it to keep the to make you understand the process, but there's an important consideration here. So we are going to have a look at it, and so let's see what is important about this EP upper and EP lower. Right. So for that, I'm going to look at, I'm going to draw something and show you. But before that, I would like you to pay little attention to the graphics. So, for example, you can see the right. Just look at this diagram. Just look at this diagram, and here you can see an upper boundary here. Then the actual boundary here, and here you can see a lower boundary. So here you can see E minimum is the blue, that is here. That means, you know, we can't have the cable beyond this point. And then we also have something called Emax. We can't have the cable beyond that point. And then you can see this red color one, that is the upper limit on ES profile. And you can see the light blue one, that is the lower limit on the ES profile. Lower limit. Right? So now we have to make sure we fit a cable inside that. And you can see we have done it pretty well, except at this location. And here you can see there's a minor violation, but not a major violation, only a small violation here. And here we are again getting there. So now this is ES profile. And the moment you know ES, you can find EP profile. And this is profile. And if I make it slightly bigger for you to have a closer look. Right. Now you can see the moment we know ES, we can find EP. The reason we already know the secondary moments. And you can see it's a matter of just writing one equation. EP is equal to ES minus M2 over RP. So the M2 is known, pre-stress is known, loss ratio is known. So finding EP is just a simple exercise. But you can see this EP is going outside the B. It doesn't matter. EP can be outside the B. But what is important is ES has to be inside the B. Right. Now let's look at the effect of this EP and what is this condition for finding fitting a bending moment diagram inside the limits. Okay, so we are going to see what is the special condition that we have to satisfy. Now, last time I told you this bending moment diagram that you can see here is a concordant profile, which means one generating 0 secondary moments. One generating 0 secondary moments. So basically, we are talking about a series, right? And we know if you take a line and mark these numbers, -2, -1, 0, 1, 2, like that. Now we are concentrating on 0. We are concentrating on 0, and we have to fit a curve inside two limits. Which means if we are to have 0 in between, if you fit a cable profile at the upper one, you should get a positive value for secondary moments. And when you fit it at the lower limit, you should get a negative value. Then only you can find a 0 in between. A 0 in between. Because we are saying we have two limits. And if I fit here, I should get 0. Then if I fit here, I should get something positive. If I fit here, I should get something negative. So basically, I'll stop share. So what we are saying is we are having 0, and so we in a line. If you are concentrating on 0, if we fit the cable at the upper limit, we should get a positive value. If we fit the cable on the lower limit, we should get a negative value. Then only we can have 0. Now let's assume another situation. We are looking for 0. That is 0, 1, 2, 3. Now let's say when we fit the cable at the lower limit, we get a value here. When we fit the cable in the upper limit, we get a value here. What will happen? We will never ever get a 0 in between. That means if we do not satisfy a condition like this, we are not going to unable to fit a cable with a concordant profile inside. You can try to fit a profile for 1 year, you will not get it. Why? Because that's a condition that has no answer. That has no answer. Right? So which means now we are getting an additional condition section. Okay. Now we are getting an additional condition which says if we are to get 0 or concordant profile, 0 secondary moment or concordant profile, then we have to select a pre-stress large enough so that when you fit upper, we get a positive, and when you fit it lower, we get a negative. So we have to see the secondary moments that we get, and we have to make sure that we satisfy a condition like that. Or it can even happen other way around, but you know, whatever it is, one should be positive, other should be negative. If both are positive or both are negative, then there is no way we can fit a 0 in between. We can fit a 0 in between. So that is the important thing we have to see. So now I'm going to show you this numerically so that you know we can easily ensure that we satisfy this particular condition. So I'm going to share the spreadsheet, and what we do is to ensure that we have fulfilled this particular condition. What we do is when in the spreadsheet we perform few calculations, right? Now you can see we have EP upper, EP lower, and here we have this so I can try any value. Let's say I try 22,000, 22,000, and now everything has changed. And when I try 22,000, you can see, look at the ES profile. See, now we don't have a feasible. So that means 22,000 is not going to work. Not going to work. So now we can try 23,000. We can try 23,000. See whether it works. Looks like that it might work. Yes, Here there's a small feasible region. Here you get a small region. Here I think might not be satisfactory because it's marginal. So what we do is now we'll try 24,000. So what happens now? Here you can see, here it's okay. We have plenty of region. Here it's okay, plenty of region. Here also not bad. We have some region. Here looks like that we are just there. We are just there. And here it's okay. But this may be still struggling a little bit. So I might consider 25%. 25%. Now let's see what happens. Here it's okay. Here it's okay. We have plenty of space, plenty of space. Here it looks now, although it's narrow, but we are okay. We are okay because this blue line is definitely below the E minimum value. Definitely below the E minimum value. You can see this blue point is definitely below this value. So it's not a problem, right? So here you get plenty of area. Here it's a marginal case, a tight case. And you can see that could be the reason why I could not get this right at this particular point, because I'm having a very thin region in this area. Then you might think, okay, this all fine, this all fine. And I should be able to find a bending moment diagram that fits this. But now I'm going to show you that it is not adequate. Even 25,000 is not adequate. 25,000 is not adequate. Now let's see what has happened. So to do that, what I see is, so basically I have a EP profile that can go like this. So I have an EP profile. And what I do is, I'll assume that I have fitted the cable here, or the line of thrust here. I will assume that I have fitted the line of thrust. So what I do now is, I will calculate the M2 values corresponding to this. I will calculate M2 values corresponding to this. How can I calculate the M2 values? Can you remember last time we used this matrix where I said what we have to do is form this matrix 1/6 twice L1 plus L2, L2 twice L2 plus L3, and so last time we did this equation M2 2, M2 3, integration beta 2, PE dx, beta 3, PE dx. So this is what we did. So basically, to find this right hand side of the equation, we need integration beta to R T E D X. To find the right hand side of the equation, we need beta 2 R P E D X. And I told you what is meant by that is, if you take 3 supports like that, we have a cable running like that, and beta will vary like that. This is E, this is beta. RP is constant, so you can take it out. So what you need is RP multiplied by integration E beta dx. So that means we have this and we multiply E by beta. We are going to get diagonal like that. Find the total area of this diagram. Find the total of area of this diagram and find the area and multiply it by R. Right? Multiplied by R. So that's what we have to do. Now let's see how we have done it on spreadsheet. So let's see how we have done it on spreadsheet. So what I have done here is, here you can see I have got EP, then I have multiplied by RP beta 2 EP, but I have got 2 values for upper and 2 values for lower, and you might wonder why. I'll stop share just to explain that. So basically, we are considering a beam having 3 spans. So we have a cable profile going like this, and so I want to find M2 2 and M2 3, and then that means I will have, for each limit I will have 2 beta values. This is beta 2, this is beta 3. So if I use those, so similarly, so 2 for upper limit, 2 for lower limit, 2 for upper limit and 2 for lower limit. So that's why I get 4 equations. Right? So if I share now, here you can see for upper limit, I need 2. One is beta 2 varying from 0 to 1, 1 to 0. Beta 3 varying from here nothing, it's not applicable. 0 to 1, 1 to 0 over this. And similarly, I have to find the secondary moment due to lower limit. So that means I need the addition of these 2 areas as well. And based on this, we can use the Simpson rule. We can use the Simpson rule, and here you can see the Simpson rule has 1, 4, 2, 4, 2, 4, and so on. And I explained it last time, but I'll briefly explain it now. And in Simpson rule, what we are saying is, if you have function, this H1, H2, H3. So this area is H by this H by 3, H1 plus 4 times H2 plus H3. And then you get this H4, H5. So this particular area, you will get H by 3, H3 plus 4, H4 plus H5. And then when you add those three, you can get H by 3 out. Get H1 plus 4 times H2 plus 2 times H3 plus 4 times H4 plus it will go on like that. So this coefficient, Simpson coefficient is 1, 4, 2, 4, 2. Goes on like that. So just one moment. So basically, if you look at Simpson rule, here you get H1, H2, H3, S4, H5. So the area of this particular one, is given by this equation. And the area of this one is given by this equation. So the total area is H by 3, H1 plus 4 times H2 plus 2 times H3. Here you can see H3 and H3, 2 times H3 plus 4 times H4. So you get this Simpson rule coefficient. We call it S, varying as 1, 4, 2, 4, 2, and so on. So we are using Simpson rule to find the area. So I'll share again. Now you will see the reason for this equation. So here I have beta 2 varying from 0 to 1, 1 to 0, correspond to the second support. Beta 3 varying from 0 to 1, 1 to 0, correspond to the third support. And then this Simpson coefficient is 1, 4, 2, 4, and so on. So if I want to find the area, I have to actually multiply by all these, so these values by R, P, beta 2, EPS. So if I look at one of the equations, just look at this equation. Here you can see we are multiplying D13, which means, this one. Here you can see I am multiplying D37. D37 is beta 2 multiplied by D39. You can see I have multiplied by this coefficient. Then D35 upper limit, and D27 P trial. D28 is R. So these are P, beta 2, EP upper, but when we here this S factor is also there. So we multiply by all, and then what we do is we come to this side, right, and get the addition of all these, because we are looking at the total area. So you have to add all these numbers and write it here. Right. Similarly, I have to add all these numbers, whatever one comes, and write it here. Right. So after that, what I have to do is I have to find the secondary moments, M22 upper, M22 lower, M23 lower, right? Okay. So let's see what happens, right? What happens? So now here I have selected the pre-stress force of 25,000, and using these values. Now, if you look at the spreadsheet, here you can see that I have got these values, right? I have got these values, and then this is AD So you can see it's a summary of all these numbers. And if you look at this particular K, it is AD40, right? So I have the addition. That means, if you look at these two numbers, if you look at the matrix, just see these two numbers, and I'll stop share. What is meant by those two numbers will be, so I have the matrix 1/6. So I have this matrix M22, M22, 3. And what these numbers means is those two numbers. So you can straight away find the second moments generated. And so by inverting the matrix, you have to invert the matrix and find the second moment. So I have actually done it here. And if I come here you can see I have got these values 1761 and 280, and they have come from right. I have actually calculated them, and here again you can see I have calculated those values, and so basically what I have calculated here are the resultant secondary moments after inverting the matrix. Now let's see what happens the moment I just look at these numbers 1761, 280. These two are positive. Here one is negative, one is positive. And let's see what happens when I make this 26,000. 26,000. Just look at these numbers. The moment I change it to 26,000, what happened? Both these became negative. Both these are positive. Now, can you remember I told you the condition? If you want to have a 0, one has to be negative, other has to be positive. But when I use 25,000, you can see at one support, it is okay. At one support, it is okay. At the second support, one is negative, other one is positive. But at the second support, both are positive. That means I cannot find the 0 in between. That means 25,000 force is not sufficient. So if you look at this profile, here 25,000 is sufficient, right? 25,000 is sufficient. But according to the condition, for existence of a line of thrust, 25,000 is not sufficient. It has to be 26,000. So what you have to keep in mind is, if you don't do this check, you might be chasing a set of limits in which you can never ever fit a bending moment diagram. So to avoid this problem happening, when you are doing the calculation, while selecting the pre-stressing force, first we look at the graphics and see how much is needed. And the moment we select a pre-stressing force, we should do this additional check where we see whether when we fit a cable at the upper limit of line of thrust, at each support, we should get a minus answer. When you do fit it at the lower support, at each support, we should get a positive answer. If you are getting both negative or both positive, there's no 0 in between. That means the pre-stressing force selected is insufficient. The pre-stressing force selected is insufficient, and you are trying to fit a bending moment diagram to a set of limits where no bending moment diagram ever exists. So whatever the load combination you select, you can never ever fit a bending moment diagram into those limits. Even if you try for 1 year, you will never fit it, because there's no single bending moment diagram that can be fitted inside. But if you are going to check this limit and make sure pre-stress force selected is large enough, For both to be negative and both to be positive, that means at support number 2, we have a 0 in between. At support number 3, we have a 0 in between. And again, you can see this is only a very marginal value, minus 60. This minus 2102 is substantial value, but here it's a very marginal value. So again, this is a very important condition, because otherwise you can run into you are designing a beam, you have selected a wrong pre-stressing force for which there's no answer, and you struggle for long time without getting an answer. On the other hand, you have selected a pre-stressing force for which there's an answer. Very quickly, you can find a set of loads that will generate a bending moment diagram using SAP 2000 with little bit of trial and error. Right? With little bit of trial and error, it will take about half an hour for you to fit a bending moment diagram, because there are plenty of solutions that can be fitted. On the other hand, you select an inadequate pre-stressing force, there's no answer, and you keep on trying. When you fit, when you bring the bending moment diagram in one region, it will violate in the other region. So you will be just struggling a lot with the SAP 2000 and this spreadsheet, because you are trying to find an answer that is not existing. So that's why it's very important that we do this particular check when you are doing a design, because the force of 25,000 that actually shows that it's perfectly okay with the profile, perfectly okay, except here it's also marginal, but it's adequate. But there's no answer. There's no answer. At the moment you come to 26,000, there are plenty of answers. So you can select the pre-stressing force. Manduga, is that correct? Is that clear?
Yes, sir. That is fine.
Right?
Yeah.
Right. So basically, there are special conditions that you have to satisfy. And we are looking for concordant profile, which means a profile that generates 0 secondary moments at each support. So for that to happen, there should be the upper limit and lower limit should be, one should be positive, one should be negative. Then only we can find 0. That if you are getting both positive or both negative, at least at one support, that means the pre-stress force selected is insufficient. So that's what you have to keep in mind. So basically what this says is, you cannot select the pre-stressing force from the Magnell diagram alone. In simply support case, if you select a pre-stressing force inside the Magnell diagram, absolutely no problem. It will satisfy the limits. Whereas in continuous structures, you have to go one step further and ensure at each support, upper and lower limits will give one positive and one negative, and then only 0 is in between. So that's how you have to look at it. And then, so that is one condition. That's very important condition that we have to fulfill. And I'm going to show you another important aspect, and that is related to construction. So if you have any question, please post it on chat so that I can answer before I go to the next step. But the important thing that you have to keep in mind is, it's a rule. The rule is, the pre-stressing force you select based on the Magnell diagram may not be sufficient in a continuous structure. You have to look at it additionally, and that is to make sure concordant profile exists at each support. That means the secondary moment generated at each support due to a concordant profile should be 0, and that can happen only if the upper and lower limits are going to give us plus and minus answers. Otherwise, you can never have a zero in between two minus quantities or two plus quantities. If you want to have a zero, one parameter has to be negative, other parameter has to be positive. So we have two limits. One is the upper limit, the other one is the lower limit. And we calculate the pre-stressing force due to these two limits. And if you are going to get minus and plus at each support, we are through. But if you are going to get plus at least at one support, that means the pre-stress force selected is insufficient. So that's what you have to keep in mind. So you basically, when you are if you are a good design engineer, always you will develop set of rules. The rules. So for example, today at the beginning I wrote a note. These are the rules. These are the rules. But you can see these rules alone are not sufficient. Then you have to add few more rules. What are the rules? So you can find the PRP, but before this, check the adequacy of P. Check the adequacy of P, right? Before we venture into fitting a bending moment diagram, we should see whether this P selected is sufficient or not. If it is insufficient, but pretty close to the actual value, but still insufficient, it will be extremely difficult or impossible for you to fit an actual bending moment diagram within the limits. So you have to be very careful with those ones. So always in design, my way of doing things is I always first learn the method, then I will convert it to a set of rules, so that we can easily memorize the method. So we know the method because we have developed our own rules, and so we can easily store it in our brain. Otherwise, what happens is, you are a good design engineer. Whenever you are given a task, you have to refer your previous notes. But on the other hand, what we do is, we look at the method, we convert it to a simple set of rules, and then we store it. So we are stored in the rules. The moment you store the rules, even a very complicated design process can be broken into a simple collection of rules, right? And that way you can easily become a top-class design engineer, because whenever a question is asked, you don't have to refer any notes. What you have to do is just recall your rules, and using the rules, now you can start answering. So that's the way I actually do design. So for example, I can do any kind of design without looking at a code, because almost a lot of rules in codes I have converted to simple rules, and I can just keep on designing without looking at a code. So that's why I wrote this method. So now you can see the whole complicated method is explained as a set of steps, and at each step we are actually telling something to be done. And now, after doing all these things, today's lecture we found, okay, now this is what we have written in red color is based on what we have learned last time. Now we are getting some additional checks as well. So that's one important thing. And there's nothing in the chat channel. So because of that, I will move to the next step, and that is construction sequence. The effect of construction sequence. So page number 5, constructions. Okay. So 6. Okay, now let's look at construction sequence. Construction sequence. Okay. Now, how are we going to construct a bridge like this? You can see. Say this is 40 meters, this is 50 meters. These are not simple spans. These are massive spans. Now, how can we construct it? That's an important question. So there are many methods, but one possible method is, now we have this. Set up a truss. Like that. Then you will ask why I go beyond this level. Let's say I have cantilever overhang of 5 meters. Why do I do that? Now we know if we have a beam like that, now sometimes we can't have the cables running all the way this, right? Now, if you want to stop a cable, what is a better location? Oval support is fairly congested. So you would prefer not anchoring at the top slab level, but you might prefer to anchor little away from the support so that you can anchor it in the wall. Anchor it in the wall. So if you are going to use this kind of method, then what will happen? First, we'll have the truss here. What is the next step? You cast the beam, move the truss like that. Move the truss up to the next one. Then you are going to pass this, and move the truss. And then you cast the last. So if you look at construction sequence, I mean, practically, it's not possible to construct at once. We have to first complete one span, then only we can move to the next span. So how can we depict this in our analysis? So what is this? First step. What is the shape of the bending moment? What are we going to do next? Here you can see going that way. Now we are going to apply the load here. Now at this moment only the red moves. So what will happen? What will happen? We get a bending moment diagram. Now I have the full beam, last leg done. And I have load only this stretch. And I'm going to get so the total bending moment diagram will be at this. Then what is the final bending moment diagram? What is the final bending moment diagram? Final bending moment diagram will be and goes like that. We go like that. Then you will ask, what would have been the monolithic bending moment diagram? It will go like that. Now you can understand why this secondary moments will be lesser, because there's lack of continuity. So this has lesser fixity. So this will sag more. In the first one also this will sag more. So continuous one will have a higher sagging moment support than this one. So this is the monolithic. What are we going to call the low one? We call it as built. As built. It's not monolithic. That's how it is built. Then you will ask, okay, so why bother? Just use the as built. Only thing is, you have to look at the construction sequence and generate a bending moment diagram which is relevant to the construction sequence. But the problem is not as simple, because you can see now, if you look at one diagram like this, you get certain curvatures. Now what happens when you are doing construction? When you are doing construction, I need not have the same curvature. Why? Because I have considered only this. So the curvatures can be different. Because curvatures are different, now we are casting not the monolithic, so we will have something called locked in stresses. And what happens due to when there's a stress on concrete? Stress on concrete means creep. If you put a stress on concrete will creep. That means concrete will change the dimensions while under the load. So it will creep. So when concrete creeps, what happens to this bending moment diagram? Where is it going? It will start moving closer to the monolithic diagram. So you will find, although you calculate very accurately the bending moment diagram, due to the construction sequence, it is not going to stay as it is. Due to creep of concrete, it will start gradually moving towards the monolithic condition. And you might find that, so this, let's say this 100, the difference is 100. After some time, you will find the difference is only 40. Most of these locked-in stressors have been relieved automatically by the structure, because by doing this construction sequence, you have achieved the monolithic structure in stages. So it must adjust the curvatures so that it will look pretty much like a structure constructed at this. So curvatures will change. How the curvatures change? Whenever there's an additional stress or locked-in stress, concrete is a material that is not very strong in creep. So concrete will start changing the curvatures. And if you construct the stressors, the actual stressors due to dead loads, say 50 or 60 years after construction, you will find that they have actually moved closer to the monolithic diagram. So that can happen. So that happens due to creep of concrete. So how are we going to take this into account? So what this basically says is, now although you are calculating the bending moment by considering the actual condition, it is going to be valid only initially. With time, this bending moment diagram is changing. Those are little tricky situations because we like bending moments, shear forces to remain what we have calculated. But here what is happening is, this is the monolithic diagram. This is the as-built diagram. As-built. As-built diagram. Now we are, so I did not mention anything, so you would have thought I would have used this as the dead load moment diagram. So what I actually did was I use this for MB boundary. I use this for MA boundary. So basically what I did was I changed in such a way that when I calculate the maximum moment, I use this boundary because during the construction and after the construction, for some time, this will be the governing. After that, it will start moving towards the mountain. So after a long time, what is the diagram? That is blue color. So immediately after construction, dead loads will, or self-weight of the beam will give a bending moment diagram marked in red color. After 50 years, it's going to give a color given by blue color. So there's no way I can actually take both into account. So what I have done is, to calculate the maximum moment, I use the lower diagram. To calculate the minimum moment, I use the upper diagram. I use the upper diagram. So I can show you what happened on the spreadsheet. So I'll share it. And you can see what happened. Here you can see now I have actually calculated the, can you see monolithic and as-built, two different diagrams for the self-weight. So this is the self-weight moment values if I have done the construction at once. M as-built is the bending moment diagram that I get when I take the actual construction sequence into account. Then when I calculated this MA, and if you look at this diagram, and you can see I have considered monolithic diagram for MA. Just look at MB, you will find I have used the as-built diagram for MB. I have used the as-built diagram for MB. Why? Immediately after construction, what governs is the construction sequence built one, CESC sequence based one, that is as-built. After a long period of time, what is applicable is monolithic. And if you look at the direction it's moving, it will start at as-built, which is the lower diagram. It will move towards the upper diagram, that is monolithic. So that means when I want the maximum bending moment effect, that is MB, I would use the lower boundary because I'm going to get a bigger bending moment. On the other hand, when I want to calculate the minimum moment, I will use the blue color one, that is the monolithic diagram. So that way, what will happen? I mean, I will get a slightly broader a moment range than the actual. So when the moment range increases, the pre-stressing force and all the other things will also increase slightly. But it's no harm, because now we have taken the practical construction sequence into account when you are doing the calculations. Otherwise, if you just use either the monolithic or as built, then you might run into trouble, because your design will be valid only for initial conditions. After a long time, you will find now most of your calculations are not valid. On the other hand, you design it for the monolithic one, your calculations will be valid only after a long time. Say 50, 60 years after construction, your calculations are valid. So to make sure our calculations are valid now and 50 years, we do a small trick. The trick is, when I calculate the maximum moment, we'll use as built. When I'm calculating the minimum moment at a given section, I will use monolithic. So that's how we do the calculations, because we cannot just say, like in a simply supported case, we are not going to worry about concrete properties. So you have to actually worry about concrete properties like creep, shrinkage. So those must be looked into. Why? Otherwise, because this is continuous, we can have locked-in stressors. And these locked-in stressors are going to change the curvatures. Even if you don't do anything, still those curvature changes will occur automatically, because there will be plenty of locked-in stresses, the stresses that are trapped. So when the stresses are trapped, those stressors will try to do some adjustment. And the adjustment is actually the bending moment diagram due to dead loads moving from one extreme to the other extreme. So that is something important. Bandhu, can you understand it?
That is clear, sir.
Yeah, that's clear, right? So you have to consider the construction sequence also into account. You cannot blindly say, okay, I have done it and I can't do anything about construction sequence. That is not applicable. But again, the good thing is all these problems are only for this very complicated continuous beam bridges. Right. So if you look at, but I cannot be specifying the secondary mode based on both. So what I have done is I have actually selected the secondary moment based on which one? Dead load moment diagram, as built and monolithic. I think I have considered it based on as built. Why? As built is the one that is applicable immediately after construction. So I have used M2 as a function of as built. I will use M2 as a function of as built, and a monolithic condition will come a long time afterwards. So those are the important things I wanted to highlight today. And the other important thing you can see is here, when you look at these beta values, beta 2 is the beta value that has varied from 0 to 1 and 1 to 0. And if you look at all these things, I have actually entered those values manually rather than writing an equation, right? So if you are a big fan of Excel, you might write with an equation, but here I have just what I have done is I have just divided it into 10 and I have entered these values manually, right? So these S values are also entered manually. You can see at the top only 4, all these appear, and 0.625 also appear. So I did not write any equation, any equations, but I just entered them because this is a big design. So spending 3-4 minutes entering some data is not a big deal, because we are going to deal with a lot more complicated things, right? And then the other important thing I can show you is now EP actual. Right, if you calculate this, so if you want, you can actually calculate the second performance due to EP actual as well. And what are the answers you should get? You should get 0. If you calculate, I have not done it, but if you calculate, you will get 0. The other important thing you can say is calculate the M2 values for actual profile that you have converted. And here I have done that. I have done those 2 values. And now you can compare actual with you can compare the actual M2 values are 7967. 7967. See, these are 7967 and 7114. 7114. Here. Okay. So those are the values I have selected. And then here you can see what is generated comes very close to that. So at the end of all your calculations, you'll select the EP actual, convert it to ES actual, and then calculate the actual second performance generated, compare it with what you have assumed. They must be extremely close. They must be extremely close. And those are the additional checks you can do. So you can see this spreadsheet based calculation. If you have understood the process, then you can easily manipulate this kind of program and design very optimized ones. So the spine beams can be optimized a lot when you start using this particular method, because we are in full control of the design process. And you can see the whole design for a 130-meter long bridge using 2 box girders is just this particular spreadsheet. That's all. Right. The whole big process has been, captured onto a simple spreadsheet. And that is the beauty, because you can see there are so many extra things we have checked while doing this spreadsheet. So, Bandhu, any chats, anything that you like to know? Any questions you like to ask?
Seems there's nothing in the chat box.
Yeah, there's nothing in the chat box.
Yeah.
There's nothing in the chat box.
Yes, sir.
Yeah. I mean, have you understood it fully?
It is clear, sir.
Yeah. Yeah. Today, what I showed was, just by, the design of continuous beams, they differ significantly from the simply supported ones. That's what you have to keep in mind. Design of a continuous beam, pre-stressed concrete beam, differs significantly from a simply supported one, because simply supported one will not have trapped moments. It will not have trapped stresses. So whatever the bending moment diagram you get initially will be valid after 50 years time. but not in continuous. What is applicable initially after the construction may not be applicable in 50 years time. Second condition is, just because you have got a zone which is valid throughout the length of the beam, still using the Magnol diagrams, it does not mean it is going to be adequate. You have to check whether it's adequate or not by using the EP upper limit and EP lower limit. So those are the very important things I have highlighted, because if you don't know these two things, your design can be rejected because you have just found some stresses and all that. But any person knowing the design method will say, okay, your design is incomplete because you have used the wrong pre-stress, initial pre-stress. Or he might say, okay, your design is not true because you have considered monolithic condition for dead loads, and you have done your design without worrying about the construction sequence. And the bending moment diagram that you used should have been an envelope, not a diagram. So because you did not use an envelope, all your calculations are wrong because the moment range is wrong. So what happens is, because we are using lower boundary to calculate MD and upper boundary to calculate MA, you are actually adopting a proper moment range. Whereas if you don't do it, then somebody can say, okay, your design is valid only at the beginning or at the end. It's not valid throughout the lifespan of the bridge. So then you might have to go back and do all the calculations. So that's why these few additional steps available in the spreadsheet would be important. But again, you can see in the spreadsheet, even with all these intricacies, calculations, checks, still it has only 52 lines. That's only 52 lines. And the other direction is the length of the bridge. So length, if you want to shorten the length even for a longer bridge, you can reduce the number of sections. But here I have been very generous. Every 5 meters I am having a section. Every 5 meters I have used a separate section so that I could easily generate the actual shape of the bending moment diagram. Okay, Bandhuka, shall we stop then?
Okay, sir.
So next week, again, I think it's good if I just spend little time,
Okay.
Highlighting the proof, how I got this matrix. But I used the matrix, but I did not show you how I got it. So it's just a simple virtual work based theory that is very useful. So that's why I will show it, and then I will show you. It can be used for creep and shrinkage calculations and so many other calculations. So this method is applicable, and method can be used for any effect that is going to change the curvature. So in continuous bridges, creep can change the curvature. Shrinkage can change the curvature. So as thermal stresses also can change the curvature. So when you are calculating those effects, again this matrix-based method becomes very useful, right? So because of that reason, next week we will spend little time deriving this equation, and then there are a few other aspects like how to do the grillage analysis for a spine beam. So we have to look into all these different aspects. So and then how to apply loads that are given in BS 5400 part 4. So BS 5400 part 4, yes, part 4. part 2, the loads given in part 2, or else we have to actually see how the Eurocode based loads can be applied onto a village, so that we can find a bending moment diagram that I have used. And also I should show you with a small demonstration how to select the various load combinations, how to combine the loads manually, so that you can generate a smooth profile. So that is also something that I have not shown, so I'll show it next time. So we might need sometimes, Bandhuka, about 2 more lectures.
Okay, sir.
Right. And also I have talked to few top expert designers in the world, and they have indicated their willingness to talk, do 1 or 2 presentations. So we can actually look forward to those as well.
Okay,
and also, how about this, substructure design? I can actually show you how to do the computer modeling of substructure design as well.
That would be great, sir, if we can have a session on substructure as well.
Yeah, so I can show you how to do the modeling, how to model the piles with winkless springs, and if it is a raft foundation, how we can model the raft foundation with the when the soil is laterite and water table is high, when the water table is low. So there's a huge amount of information that is lying around, so I can cover those as well. Which means we might have to continue this lecture series for 5-6 lectures more.
Okay, sir.
But I can show you with the computer modeling how those things can be done. Okay.
Okay,
right.
That
okay. So yeah. So you can get some feedback, and we continue that for 5-6 lectures, and then we'll invite.
That means we did cover including piles, foundations, and piers as well.
Yeah, we can cover all those. Right.
Okay.
So I can show you how to computer modeling using SAP 2000, where even the soil is modeled using solid elements. That type of modeling you wouldn't have done most probably. Has anybody modeled the foundation sitting on a clay soil like laterite soil, strong soil, but a raft foundation where cover effects are lower? We can actually model the soil and the raft foundation, everything together. So there are so many options, and also you can go for cellular rafts rather than wasting a lot of concrete. You can do cellular rafts, and I can actually send you one news item recently about Mahayangana temple, where we have got a very tall Buddha statue, and we did the foundation for that using a cellular raft. So basically, I can show some of those aspects as well. So basically, we'll assume that we are going to have about 5 more lectures. Bandhu?
Okay, sir. Okay, sir.
Right? Okay, right. Okay. Very good. Okay, then, right.
Okay, sir. And on behalf of the Technical Events Subcommittee of Civil Engineering Sectional Committee, I take this opportunity to thank Professor Tisan Jayasinghe for the commitment in conducting this lecture series. We have received many positive feedbacks, not only from practicing engineers, but also from different institutions. And the lecture series has been a great service for the engineering community, as this has been uploaded to ISL YouTube channel and can be accessed at any time. Thank you very much, Professor. And further,
thank you very much.
I would like to thank the Chairman of Civil Engineering Sectional Committee, Engineer Kamala Gunawardena, for the guidance and leadership given in conducting this lecture series. Also, I would like to thank the ISL Secretariat, Publicity Department, and IT team for the continuous support. Thank you very much. Last but not least, I would like to thank all the participants. Thank you very much, and have a great evening.
Yeah. Okay. Thank you very much.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Thank you.